Okay, let's take a look at the next graph. Now, take a look at the format. We have R equals some number, let's call that A, plus some number, we'll call that B, cosine theta. R equals A plus B cosine of theta, that is a lemma-sum. Right? Now, there's some things we know about this lemma-sum. Since it is a cosine lemma-sum, if this is the pole, the majority of this lemma-sum is going to be to the right of the pole, just like it would be if we had a circle to cosine theta that passes through the pole. All right, now which type is this? Well, if you take a look at the absolute value of A, compare it to the absolute value of B, 3 is greater than 2. So absolute value of A is greater than the absolute value of B, means that this lemma-sum is going to do one of these numbers. Fake into the pole, come back out. It's going to look something like this. And the majority of it will be to the right. So, spoiler alert, this is what this thing looks like. Right? Now, again, we can talk about distance from here to the edge or distance from here to here, again, by looking at these. But you'll see in the picture that this will hold true. All right, so what I have set up is the table of points. I went from 0 to 360, and I counted by 30 degrees. Right, now, we will need our calculator for a few of these, a couple more than we did for the simple circle here. But some of these are actually not too terrible. Let's see. We'll start off with 0. The cosine of 0 is 1. 1 times 2 is 2, and 2 plus 3 is 5. Right? I mean, we can enter that literally into our calculator. 3 plus 2 cosine 0. Again, the cosine of 0 is 1. Then we have to multiply by 2. Then we have to add 3 in that order. It's got to be that way. All right, the cosine of 30 is not particularly pleasant. So 3 plus 2 cosine 30. I mean, I'm literally just entering that in as you see it right there. 3 plus 2 cosine 30. And I'm getting about 4.7. About. And again, we're plotting these, so rounding to the nearest tenth is very reasonable. Okay, 60 is actually nice, because the cosine of 60 is a half. 1/2 times 2 is 1. 1 plus 3 is 4. 90 is quadrantal, so it shouldn't be too bad. Cosine of 90 is 0. 0 times 2 is 0. Plus 3 is 3. 120 is actually not too bad. But careful, you've just entered quadrant 2, where cosine is negative. 120 has a reference of 60. So we do have to be careful here. So the cosine of 120 is not 1/2 like it was for the cosine of 60. It's going to be negative 1/2 times 2 is negative 1 plus 3 puts us at 2. All right, 150, I'm just going to go to the calculator because it'll actually be minus here. So 3 plus 2 cosine of 150. Not pleasant. It's at 1.3 roughly if I round to the nearest tenth. Okay, 180 is not bad. The cosine of 180 is negative 1 times 2 is negative 2 plus 3 is 1. 210 has a reference of 30 in Q3 now. So it should be the same as 150, which had a reference of 30 in quadrant 2. The exact same answer. So it should be back to 1.3. And then 240 should be the same as 120. 270 is quadrantal. Cosine of 270 is 0 times 2 is 0 plus 3 is 3. 300, okay, now we're back to positive territory because we're in Q4 where cosine is definitely positive. Cosine's positive in quadrant 4. Reference of 60, so I'll go back to what I had for 60, which is 4. That'll be a reference of 30, which was roughly 4.7, and that should be right back to the start. You notice you have some very nice symmetry here. And a lot of your polar graphs do have that nice symmetry, and you'll take advantage of that when you see this in more advanced courses, like your Calculus 2. You take advantage of the symmetry aspect. But in any event, we're plotting these things out. Let's take a look at the graph and carefully see what we get. So 5, 0. So 1, 2, 3, 4, 5, 0. 4.7, 30. So 4.7, 30. 460 would be there. 390 would be here. 2, 120. Again, since everything's positive, my r and my theta are both positive. I'm just using these markers out here. But I can't talk and plot at the same time. 2, 120, 1.3, 150. Let's find 1.3. Notice we're kind of coming into the pole, but wait, 180. Nope, that's as close as we get to the pole. In fact, 1 away, and it's not a coincidence. 3 minus 2 is 1. That distance from where that dimple is to the pole is 1. Distance from here to that point is exactly 3 plus 2, 5. All right, finishing this off, it's going to be pure symmetry. I'm just going to plot these as if this were folded vertically. All right, so 2, where am I at? 1.3, 210, sorry. 1.3, let's just keep going, 210. Just trying to mirror that point. 3, 270, 2, 240, sorry, missed that one. 2, 240, where are you at? 2, 240, 3, 270, way down there. 4, 300. Let's make sure I'm on the right circle. 2, 3, 4, yes. And 5, 360. I'm missing one. 4.7, 330. Come on. There's 330, 4.7-ish. Right there. What we got? Actually, let me draw it as it was being plotted. Because this is how your calculator would draw it out. It'd start there, and it'll work its way around, fake into the pole for that dimple there. And there you go. This is type 1 limmason, where the absolute value of A was greater than the absolute value of B. You get something that fakes into the pole. All right? Well, let's try a different limmason here. Dare I? Yes, I dare. Let's just erase our R's here. That was easy. All right, so which one did I picked up? How about 2 minus 4 sine of theta? All right, let's kind of map this thing out as much as we know. All right, now again, it does have the format R equals A plus B sine theta. Yes, I see the negative, but your B is a negative plus that negative, right? So it is a limmason. Which type is it? Well, take the absolute value of 2, take the absolute value of 4. The absolute value of A is now less than the absolute value of B, which means you're going to have a limmason with an inner loop, right? So this thing is going to resemble this picture I'm about ready to draw. If that's a pole, we know it's a sine. A sine has most of the limmason either above or below the pole. Since the B value is negative, this is definitely going to be below the pole. So how this is going to plot, not sure the general direction here. Let's just go around. It's going to come around, make an inner loop, and then come back out. Now, that is probably not the direction it's going to go. I don't know. We'll find out. But the idea here is it's going to look something like that. Goes through the pole. And what we can also say, advanced stuff, I know the distance from here to the outer edge is going to be a grand total of 6. And I know the length of the inner loop is going to be 4 minus 2, or 2. So distance from here to here is 6. Distance from here to here will be 2. I mean, we got this thing pretty much mapped out. We just got to get the points and make this happen. All right, so again, we're going to need our calculator here for a few of these. Okay, starting with 30. Starting with 0, actually. Sine of 0 is 0, times negative 4 is 0, so that's just 2. 30 is a half. Negative 4 times a half is negative 2 plus 2. That'll actually be 0. So that's going to go right back to the pole. 60. Let's see. Sine of 60, not pleasant. Come on. There we go. All right. 2 minus 4 sine 60. Get negative 1.5-ish. It's actually negative 1.46. Okay, 90 is nice. That's 1. 2 minus 4 is negative 2. 120, again, we're in quadrant 2, reference of 60. Should be the same as that one, so negative 1.5. you'll have symmetry going across, a vertical line of symmetry for this one, unlike the last one, which was horizontal with cosine. All right, 150, reference of 30. In quadrant 2, where sine is still positive, so it'll be the exact same answer. 180, the sine of 180 is 0. It'll be back to 2. Okay, 210, we're in quadrant 3, where sine is negative. This is going to be a new value. So 2 minus 4, sine of 210. Wait, that's negative 1/2. I guess I could have done that one. That one comes out nice. 210, reference of 30, so that's negative 1/2 times negative 4 is positive 2. 2 plus 2 is 4. Shame on me. All right, 2 minus 4 sine of 240. That's going to be a different one. That's 5.5-ish. 5.5-ish. 270 is negative 1, so that's positive 4 plus 2 puts us at 6. 300, you're in quadrant 4, but it's a reference of 60, so it should be that 5.5 again. Same as quadrant 3's 240. 330 should match up with the 4, and 360 puts us back to the start. All right, what's left to do? Lot it up. Here we go. 2-0 starts here, and then it connects to 0-30. Now, that's the only tricky part. We know a limacon doesn't have a flat part to it. It has what we would call a dimple, but this one actually has to curve around. You say, well, how would I know? Well, if you pick a value between 0 and 30, like 15 degrees, you will actually see that it should work. So, just to show you for this sake, I was just going to fake it, but let's actually put in 15 degrees. So 2 minus 4 sine 15, just so you see that it does dip around. So at 15, it's actually 0.96. I don't know what you call that. 0.96. So 0.96, 15 degrees would put us right there. So you can see it just goes a bit above. Just a little bit above. Don't make it go flat across. We know that it is not what it looks like. All right, let's finish carving this thing out. So negative 1.5, 60, we got to be careful. Negative 1.5, 60 in the counterclockwise fashion, which would be equivalent to our 240. Was it 1.5? Yeah. It's not as much fun as it looks. Right, negative 290. So negative 290. You can see what it's doing. It's coming around here. That's the edge of its inner loop, and then it's going to keep going. Negative 1.5, 120. Which would be like a 60 or a 300. You can see the symmetry of that inner loop. And we'll come around here again. Where are we at? 0, 150. So 0 puts us back at the pole. 2, 180. 2, 180. And again, it's going to curve up the same amount as you see over here. 4, 210. 210. You can do this. 210, 5.5, 240. Should be safe the rest of the way here. 5.5, 240. Sorry, 1, 2, 3, 4. 5.5, 240. Here we go. 6270. At the very bottom of my graph, 5.5, 300. There, 5.5, 300. 4, 330. And 2, 360. 2, 360 is right back there. So this is how the calculator would. Nice job. Carve that out. I'm way off at the 330. I can tell already. Where were we at? 4, 330. So 330. 1, 2, 3, there's 4, 330. All right, there's your limacon with an inner loop looking just as we thought it would.